Once again, we're in the PLC Professor's workshop. We're going to discuss the next lab project. There's really not a lot to be said about this next lab project. We are continuing to fatten up, if you will, the code. In other words, we just keep adding features, possible functions that you would have in the real world to the code, discussing why we're programming it the way we are, and then demonstrating it. So let's get after this. Here we are back with our challenge. Where we left off in the previous video, it got to be over an hour long, so we decided to stop and start a new one. In the last video, we discussed these 4 rungs of logic. And a quick refresh in case you have had some time lapse between the end of the last one and this one. The way this logic works is real simple. We have the photo eye, true if on, true if off. So we really have 2 rungs of logic here in one. In a sense we do. You can't do this type of code writing with RSLogix 500 or MicroStarter. So when the photo eye is blocked, see right now that's true because the photo eye is not blocked. When the photo eye is blocked, it starts this timer. After 1 second, this bit comes on. When that bit comes on, because this counter has not counted up yet, this is true. So see, we have the debounce done bit on both sides. So when it's done, this is a true path to keep the timer enabled and done. And it just sits there. And when the carton leaves the photo eye, this stays on. This bypasses it. This is an OR function. This logic is all true, keeps this done. And when this goes false, this keeps the rung true, and because this then goes off and becomes true. Now I realize you're looking at it and it's true right now. That's because it's not true over here. So remember, this goes true, this goes false. They can't both be true at the same time. And that gets the timer done and bypasses this instruction. On the scan where this instruction is false, this one's now true. But the rung is still true out here. Because that's true, it counts up. It increments by 1. And then on the next scan, because the count up bit is on, that makes this go false and the whole rung resets. These 4 rungs are really identical, except that we have now integrated these 4 together for 3 conveyors. And when we count a carton or object onto conveyor 1, we count up here. When it arrives, it travels off of conveyor 1 onto conveyor 2. See, conveyor 2 entrance. Then the same thing happens again, and it counts a carton or object onto conveyor 2. But it also counts one off, countdown, conveyor 1 count. So this rung counts cartons onto conveyor 1. This rung counts them onto conveyor 2 and off of conveyor 1. Consequently, this is for conveyor 3. It counts them onto conveyor 3 and off of conveyor 2. See? Now, when they leave conveyor 3, they're working with the exit photo eye. For conveyor 3, it counts them off. And from there, they just go on the floor or on down the line to who knows where. Enough of the review there. Clear all the counts. So we'll just select that. We don't really have a reset in here yet. We will eventually. Okay, see, now the counts are 0. In the manual, on roughly page 238, 239, we're going to run a carton onto the conveyor. If you view the production subroutine while holding each photo eye in the on state until the debounce timer is timed out and the count for that conveyor has incremented before releasing the photo eye input, starting with conveyor 1, then conveyor 2, followed by conveyor 3, and finally the exit photo eye for conveyor 3, then you will see the function, the logic function, tracking the single object through the series of conveyors. If I had a carton show up at the entrance of conveyor 1, it would block photo eye 1. Now we're not going to involve the conveyor motors. We're just going to assume they're running. Okay, so I'm going to turn on the photo eye for conveyor 1. So you see the debounce timer is done, and when it goes off, it's going to count one onto conveyor 1. Now, see, we have one on conveyor 1 here. We'll say that the motor's still running, even though that's not our end goal. We just want to pass a carton all the way through all 3 conveyors. So right now that carton is traveling to the end of conveyor 1. When it gets to the photo eye at the entrance of conveyor 2, the debounce timer is going to time out. And when it clears that photo eye, you see, it counts on to conveyor 2 and it counted off of conveyor 1. So our carton now is on conveyor 2 and it's traveling down the length of conveyor 2, whether it's 10 feet or 1,000 feet, 100 feet, it's traveling. The next place that this control system sees the carton or an object would be at the entrance of conveyor 3. So we'll turn on the entrance of conveyor 3. It turns on the conveyor 3, the debounce times out. And eventually it clears the carton, the photo eye, and it is now traveling down the length of the conveyor. It's counted onto conveyor 3 now. See, conveyor 3 has 1, conveyor 2 none, conveyor 1 none. The next thing we're going to do is encounter, the carton's going to get to the end of 3. It's going to block the exit photo eye, and after a debounce, it drops on the floor or goes on down a gravity conveyor, but you see the whole system's empty now. You need to run through your logic and test it and just keep playing with it. Now if you do something out of order, for instance, I did. So I got one onto conveyor 1, counted it on, got one onto conveyor 2, counted it on, and then I accidentally hit the wrong photo eye. So let's say right now we got a carton on conveyor 2 and your friend walks by and sticks his hand in that photo eye for more than a second. Now look what you've got. It says there's 2 on conveyor 2 because that's the photo eye he blocked and then unblocked. The problem is it counted down conveyor 1 below 0. You can't have -1 cartons or objects on conveyor 1. Now we'll add some code to prevent that. As a matter of fact, I'm going to look ahead here and see if we do that. I don't see that I did that, so I'm going to add that in even though it's not in the manual. What I would do to prevent that from happening, because having a negative number there, that's bad, because that means the next carton that comes on right there, when you count it from -1, what do you get? 0. But you still don't have 2 cartons on conveyor 2. So I'm going to put that back to 0 because we know that's an error. Now here's a thing that you can do to your code that protects against a negative number. Now if you had this running in a system and somebody walked by and put their hand in there and you had more, you had say 2 in here, 3 in there, I mean you can't protect the system from that kind of superfluous behavior by employees. It's just not possible. But you can prevent a negative count by putting in a greater than 0 on the count. If you put in a greater than 0, I'll just throw it in there, even though we have not reached those instructions yet. We'll grab a greater than and put it in here, and we'll say conveyor count 1 has to be greater than 0. The accumulate. has to be greater than 0. So I finalize all edits. Now I'm going to have to geezer down so you can see the rungs nice and tidy. Let's put a carton on conveyor 2. That was conveyor 1. So we got one on conveyor 1. I'll do one on conveyor 2. Now let's say we do conveyor 2 again. In other words, your friend walks by, puts his hand in front of the photo eye. When he removes his hand, it counted up, but it didn't count down because the cumulate was not greater than 0. That prevented a negative number in here, but that still doesn't prevent miscounts. But just for grins, I threw that in there. I'm going to take it back out. We don't want that in there. It just clutters up the code, and it's not really a good fix. But just to inspire your thinking. Now there's some more clever ways that you could use math functions to look at the quantities on conveyor 1 and conveyor 2. And if you suddenly see a count or an attempt to count up on conveyor 2 without anything leaving conveyor 1 or vice versa, you could probably put in some protection. Anyway, let's get on with business here. We went through and explained all the logic. The count up and count down instructions execute simultaneously for all intents and purposes. So it does not matter in which order you have them in the rungs. Whether you want to say that it was you counted it off of conveyor 1 before you counted it onto conveyor 2 or vice versa, it really doesn't matter. Before we continue this project though, let's pause and ponder reality. Also, we're going to start abbreviating tag names to save typing. Pt1 instead of PE, conveyor 1 entrance, conveyor 1 instead of motor conveyor 1, etc. For the logical conveyor control, we will get more methodical and write a quasi-functional specification for each of the outputs, 3 in all of which are conveyor motors. In the following logical statements, we leave out the condition of system enabled being true. It is assumed for all rungs. You need to have a developed skill of 3D visualization to be proficient at PLC programming without having a highly detailed functional specification from which to work. Now, if you have photographs and videos of the machine running that you can watch, which I don't know how that can happen unless you were duplicating an older machine, but if you're duplicating an older machine, you've already got code that runs the machine. Typically, you're not going to have anything to work with but maybe a few photographs, some of the fixturing that's finished for the machine, or a 3D image, depending on the CAD department for the company that designs the machine. Really, you're going to have to be able to visualize in 3D, 3 dimensions, to effectively be a PLC programmer. There are several phases to implementing a manufacturing process. Now we're going to kind of digress and discuss the whole process in which you want to be a part of. There's several phases. First phase is process definition. The step-by-step sequence of the handling and processing of raw materials and or components to produce a product. From that, then, you get a process design, specifying all of the physical details to accommodate the defined process, the floor space needed, how many stations in the process. If there are no human beings intervening or interacting with the process, then you need less stations. But any place that you need a human being to interact or intervene, you need a station, an operator station. Then, of course, material handling, and that is how do you get the components or the raw materials to the process and away from the process, energy sources, etc. 3D visualization needed for all of this. Imagine standing in front of a process, that is, mentally being in a position that gives you a full and complete visualization of the entire process at all times. Now this would only be possible with small processes, and that is what limited manufacturing until the Industrial Revolution is, that the operator couldn't operate a process unless he could see the whole thing. That is, being able to see every detail of the process without being able to see it with your own eyes, but rather with sensors. That's what the advent of sensors and relays is what moved processes up into larger machinery. Unless it was all mechanical, no operator intervention. Remember, if you remove the operator, then you could have large, I call them mechanical contraptions. And I do remember many of them from my days in past working at different manufacturing facilities. I remember at Ralston Purina, I automated quite a bit of a plant that makes breakfast cereal. And they had these, we'll call them packaging machines. What they did was they formed a wax paper bag, rectilinear bag, rectangular with corners, and it formed a carton, not corrugated carton, but paperboard, that was printed with the brand name and the type of cereal on it, and it formed it around that, and it worked on 6 of them at a time with an index table. If you could picture a machine that has 6 stations, and at each station it does something new. So we'll say the first station, it rolls out a piece of wax paper onto a platen, and the next station it folds it around a block of aluminum. We'll call it a dummy interior, or the shape of the interior of the carton where the cereal is going to go. It wrapped the wax paper around that and sealed it, and then in the next station it started a piece of paperboard that would then wrap around that, and then the next station it finished wrapped around that, and the next station it closed up all but the top of the breakfast cereal box. So what you have, when it came off the line to go to the next station where it was going to be filled with breakfast cereal, if you imagine taking a breakfast cereal box and carefully opening up the top, not to rip it, but open up so all 4 flaps are straight up, then reach in there and pull open the wax paper bag. They used to be wax paper, now they're more plastic, very carefully, and then open it up so it's completely wide open and ready to receive cereal. That's what came off the machine. That machine was 100% mechanical. There was an electric motor that ran it, but everything else was levers, gears, eccentrics. It was an amazing piece of industrial art to watch, and it made a rhythmical music all by itself. Well, if you go online and dig around, maybe you'll find a YouTube video of something like that. But there was no operator intervention. All the operator did was put stacks of paperboard unfolded cartons in the feeder, and it put rolls of wax paper in another place, and what came out were cartons with a wax paper bag inside ready to receive cereal. Then the operator picked those up from the chute that came off the machine and put them on a line, a conveyor system that took them down to the fillers. So there was really no operator intervention, no stations. So it didn't matter whether the operator could see every little moving component in that machine. And to get rid of the linkages, this mass of linkages and eccentrics that wear out and need constant adjustment, you needed sensors to see when the carton was ready for the next part of the process, not have it just be mechanically animated. We're trying to give you a visualization of the evolution of machinery and control systems. You need to move the product in process through each station and see when the product arrives and leaves as it passes through each station. Within each station, you need to see each device that causes the progress of the product in process at that station. This would include the individual actions of each device, cylinders, motors, you name it. At this level, you are experiencing presence and action, sensors and actuators. Unfortunately, we cannot view the actual process until it is completed. For this reason, we have to build and visualize the entire process in our imagination. We have to imagine it. The next phase, after process definition and process design, is station machine design. Mechanical design of each station and any material handling sections to or from and between stations. Energy requirements are yielded in this phase, and especially the sensors and the actuators to sense and operate the mechanical design. Again, you need 3D visualization. A good mechanical machine process designer will have a controls engineer involved during this phase to influence the mechanical design to accommodate specific sensors and type of motion, i.e. cylinders, AC motors, servo motors, etc. Out of all of this should emerge a functional specification. You see, as the engineers and the designers are going along, they're taking notes and writing down everything that they need. And at this point, because they are recognizing what specific sensors and actuators they need and making note of them, making note of the length and the definition, they are coming up with a functional specification that the controls engineer can then use to design the control system, selecting motor drives, motor starters, pneumatic hydraulic valve banks, power distribution, circuit protection, the specific controller, I/O modules, I/O interfaces, and of course HMIs, whether those HMIs are push buttons and lights, touch screens, membrane keypads, etc. It is not a good idea to start writing the controller program until this phase is completely finished, including and especially the documentation electrical drawing set. Now, somewhere in between here and the finished electrical drawing set with RSLogix 5000, you can start writing the program. Once the process has been well defined, even though the electrical prints are not done that have I/O assignments, you can start with RSLogix 5000 because of the advent of concurrent engineering. Before this, you had to have the I/O sheets from the drawing set to begin writing the controller program. With RSLogix 5000, you can write the program using base tags and alias them later to the actual I/O memory locations. And by base tags, I mean when we started, we didn't have PE Conveyor 1 entrants necessarily assigned to or alias to a module defined tag. So we just went through and wrote our logic based on what we thought we needed for sensors and actuators. In PLC programming, controls engineering, we have authors and we have translators. They don't use those terms in the field, but you understand the difference between an author and a translator. There are many who can follow a functional specification and write a program based upon that document. But if you cannot visualize it in your mind, you are like a translator who translates a document from one language to another with no comprehension of the subject that inspired that document. Now, if you could stop and ponder that for a minute, you'll see where I'm going with this. If I were to translate a document from English to Spanish, let's say that I spoke Spanish and was fluent with Spanish reading and writing, but I was translating a document on a subject that I knew nothing about. The best that I could do would be close to a word-by-word translation. The structure in one language is different than the other, so we'll just assume that that includes me putting the adjectives in the right spot, which is after rather than before the noun. So other than that, I do translate the document, and anybody reading my document would see that it basically was saying something similar to the original document, but it wouldn't be saying the exact same thing. I'll guarantee you, without the author's knowledge and understanding of the subject, the translator is not going to do the same job. Now, there are many that can do this, but give them a process to control without a highly detailed and exhaustive functional specification, and they are as lost as a flock of geese flying in a hailstorm, and that's lost. Now let's take the analogy one step further. Let's assume that there are a number of minds, that is, imaginations. We all have imaginations, and that's how we visualize in 3D. We image it, imagine it. There are a number of minds, imaginations, involved with this manufacturing process. The product engineer or manufacturing engineer, mechanical engineer, and electrical engineer. Let's assume that the idea begins with the product engineer designer, even though we know the idea for the product probably blossomed somewhere else, but the first step into making it a reality is the product engineer or designer. This idea will pass through the imaginations after the product engineer designer gets done with it, imagining it, creating some documentation, some sketches. This idea will pass through the imaginations of at least 3 more people on its way to reality. We also know that as the idea passes from one person to another, it takes on the perception of each individual's interpretation of the previous person's communication to the next person in the sequence. And that is convoluted in several ways. One is, if the next person doesn't know the last person, then they are a little bit more free. They have a little more latitude to interpret the last person's idea into their own idea that fits the description given them by the last person. If they know the last person, then they're more likely to get it a little bit more accurate, and they're more likely to ask the last person questions to clarify the documentation that came from the previous step. By the time it reaches the controls engineer, and that would be you in this case, the idea that was communicated will not be exactly what the product designer had in their imagination, their mental visualization. This is the limitation of language, communication, and visualization. Think of a language and documentation as the conveyance of ideas from one imagination to another imagination, and each successive imagination has the responsibility of applying their specific knowledge to make that idea a reality. Just like people designing cars. Some space cadet right out of art school or product design school, he sketches up a car, real slick looking thing. Nice lines, but not necessarily practical lines. So he shifts it off, and the first thing that happens is the guy that designs the chassis saying, well, there's no way I can get a chassis under that body design and provide a front bumper and a rear bumper. He has to alter it to allow for a front and a rear bumper. Then it goes to the body designer, and he looks at it and says, well, there's no way in the world that we can stamp out of sheet metal those door panels, hood panels, trunk panels, roof panels, fenders, etc. There's no way in the world we can do that in a stamping press in this day and age with the current technology. So he modifies the design to accommodate practical sheet metal work. And then the interior person gets a hold of it and makes a few more changes, and by the time it gets to manufacturing, where they're actually going to start contracting with tool makers and model houses, tool and die shops, etc., to come up with all the tooling to make all the parts, I'll guarantee you that car does not look like it did when it originally left the designer's drawing board. We all understand this. At this point, you write a program to control the process by what you can sense, see, with the sensors, and what you can move with the actuators, not to mention capturing production data with your program. You look at your sensors and your actuators, and you write a program to take the data from the sensors through some logical sequence to operate the actuators. You haven't actually seen the machine yet. You have a functional specification. We'll just let you have a drawing set at this point. You really don't need a drawing set at this point, but we'll just say you have a drawing set at this point so you can actually alias some I/O. So you carry your laptop and cable out to the build site. You look at the machine. It's not too much different than what you thought. Hook up, power up, and download the program into the controller. The first time you ever do this, in most cases it's going to be a big shock. Everything seems to be different than you had imagined it, how you had imaged it. The cause of this problem can be shared by all of the imaginations that the idea passed through on its way to your head. Then there are your shortcomings added to their shortcomings. If you have not prepared yourself for a pragmatic approach to doing this type of work before you come face to face with this reality, then accept it as the nature of the work or you will not be successful. If you're not well prepared to work with other people, not criticize other people that worked on it before you, but work with them to solve the problems, you're not going to be able to do this work. I'll guarantee you. We had a saying in the Marine Corps, and I think it's probably a civilian saying too, and I'll clean it up. Poop rolls downhill. And at the bottom is a controls engineer. The controls engineer, commissioner, debugger is the last person to see that machine and put it in a state to hand it off to the customer. Everything that's been done wrong, anything that's been designed wrong, anything that's late, over budget, is all in the controls engineer's hands, and they have to handle it. Being a controls engineer, unless you're the type of translator that sits in a cubicle and translates functional specifications into rough code, if you're that kind of a controls engineer, well, you're lost in your own world in a cubicle. But if you're a controls engineer that goes out and puts your belly up against the machine and has at it, you're going to have to develop some really good people skills, including working with people even more geeky than controls engineers, like IT people. No offense if you're listening. Personally, I like IT people. We all have a geeky side if we're doing this kind of work. And the more you work in the field on the machinery, you're a little less geeky. Never stick up your nose at geeky people. You need them. I'll guarantee you. They will pull your fat out of the fire more than once. If you alienate the geeks and nerds that you have access to, you are harming yourself. Okay, as I said, this problem can be shared by everyone involved, including you, and that you need to be prepared to take a pragmatic approach and understand the reality of this work. Hope for the best, but always be prepared for the worst. Do not expect the worst, but do not be taken by surprise when it is not what you hope for. You were a translator, translating another's communications, relaying their image into a control system with a program. But now you must become the author when you meet the final judges, the product designer and production managers. At this point in the process, if you cannot efficiently visualize their idea for comparison with what was delivered to them, you are in big trouble, and you will not be able to bring this project to a sign-off. A sign-off is where the customer agrees that's what they ordered and they're going to make the final payment. If they don't make the final payment, your company's not going to be happy, and if they're not happy, eventually they'll make sure you're not happy. We want to keep the logic for this imaginary conveyor system as simple as is possible, but with a legitimate feel to it. A real system would be reacting to sensors, moving objects in and out of the optical path of the sensors. We have to depend on toggling and push buttons if you have the digital field device simulator, switches, and our own sense of timing to simulate the interaction between the moving objects and the sensors. This is not as simple as it sounds. Let us examine several ideas for controlling how many objects are on each of the conveyors at any given moment. Again, we're on page 243, 244, something like that in the Lab Project Manual, Volume 1 of RSLogix 5000 Beginner. And on that page we have a graphic that shows two pairs of conveyors. It shows two conveyors And then the question above says, what is the noticeable difference between the two pairs of conveyors shown below? In the top conveyor set, two conveyors, has 1 PE and 2 PE. Those are at the entrance of conveyor 1 and conveyor 2. The bottom pair has 1 PE leaving the unknown space in front of it, 2 PE arriving on the conveyor, 3 PE leaving, 4 PE arriving on the next, 5 PE leaving the second one, then 6 PE to see the trailing edge of an object completely off of the conveyor. So the difference there is for photo eyes. The more photo eyes you have, the more the controller has to work with. Let's say that your objects or cartons are never less than 1 foot long. If you had a photo eye at every 9 inches or every 6 inches along that conveyor, you could sense the presence of all objects on that conveyor all the time. Well, obviously that's quite expensive. And the part that makes photo eyes expensive is not the photo eye. The actual photoelectric sensor and the cord that it comes with, and even the bracket, is relatively inexpensive. What costs is the labor to install those sensors on the conveyors is more expensive than the sensors themselves. Add to that the conduit or distribution system to bring each of those individual photo eyes back to the controller in a panel somewhere. That's the expensive part. The photo eye itself is not the expensive part. So when you get out in the field and you complain about there not being enough photo eyes, and for $20 they could have added another photo eye, you're way off base. The cost is not the electronic device, it's everything else. Which pair would you think is the easiest for which to write a controller program? The upper pair with 2 photo eyes or the bottom pair with 6 photo eyes? Well, 6. The bottom pair, the lower pair. Why? Because you have more events to work with. When you only have 2 photo eyes, sometimes you end up using timers to simulate sensors. For instance, if you know that the conveyor belt moves 1 foot per second and your cartons are 1 foot long, 12 inches long, then you know that for every 1 second, roughly 1 second, the carton will travel 1 foot down the conveyor. So if you have a 10-foot conveyor and you see the photo eye blocked and then cleared and the conveyor motor is still running, you can use a timer to determine where the carton is at on that conveyor. With more photo eyes, that becomes less necessary. We are going to write our logic for the upper pair simply because we do not have enough I/O interfaces on our controller to accommodate the lower pair. They both require 2 outputs for the motors, but the lower pair requires 6 inputs just for the photo eyes. We can't afford that. So we're going with the top pair, which is 2 photo eyes, and you have to be much more clever with how you write your code. Now, if you are just transporting objects, we'll say cartons. Most often I say cartons because a carton 12 inches by 12 inches by 12 inches cube is very easy to visualize traveling along on a conveyor. If you are just transporting objects, cartons, from point A to point B, you do not even need 2 photo eyes. In other words, the goal is just to have the cartons go on at the beginning of the first conveyor and go off the end of the second. In other words, you're just moving them. Anytime that the system is running, the conveyors are running, and anything that lands on the conveyor just goes on down the line. You don't need any photo eyes. However, if you want to move cartons from A to B and save energy, you need to sense to have photo eyes when there is something to move from A to B, thus not running the conveyor motors continuously. If you want to know how many cartons are on the conveyors, you need a sensor for an event to count up when they arrive and a sensor for an event when they count down when they depart. We can accomplish this with just one photo eye per conveyor by using the entrance photo eye to count the carton onto the following conveyor and off of the preceding. Now, if you don't have your manual open in front of you, you're going to miss a lot of what we're talking about, including the two pairs of conveyors we just spoke of. Because now we have 1, 2, 3, 4, 5, 6, 7, 8 examples of the position of cartons on those two conveyors that we're going to talk about. If you can't see the diagrams, I think you're going to lose something in the translation. Looking at our examples on page 244, 245, easily recognized, most of the page is covered with the individual steps of cartons as they move on to the two conveyors. So in the very first illustration, that's what you should be looking at right now. Carton or the object arrives at the entrance to conveyor 1. You have a photo eye, 1 PE is blocked. So logically, the decision is to run the conveyor or wait for logical conditions. Meaning that if the photo eye being blocked is all that you need to run the conveyor, then you run the conveyor. But keep in mind, there may not be any place for the carton to go. So just because the photo eye is blocked doesn't mean you can start the conveyor and pull it onto the conveyor. Now in this case, we plainly show you there's no other cartons on the conveyor. In step 2, carton is on the conveyor and has cleared 1 PE, decision to stop the conveyor or run the conveyor or wait for logical conditions. Those are your choices. We stop the conveyor, or we have another carton show up right away in step 3. Carton arrives at the entrance to conveyor 1. Decision is to run the conveyor or wait for logical conditions. Step 4, carton is blocking the entrance to conveyor 1. Decision is to run the conveyor or wait for logical conditions, meaning that once in step 3 you have a carton blocking 1 PE, the only difference between step 3 and step 4 is that if the motor is running, you are assuming the carton is moving through the photo eye continually. So carton in step 3, it arrives and blocks the photo eye. If you decide to run the conveyor, then in step 4, you have to decide whether to keep running it or to stop. Now obviously in our code we're looking for the trailing edge of the carton to stop, but still you need to think through every single aspect of what's going on in this very, very simple process. Step 5, carton is on conveyor 1 and has cleared 1 PE. Again, decision is to stop or run the conveyor or wait for logical conditions. Remember, what we're working up to is the functional specification for our conveyor motors. And the logic for our conveyor motors, when they run and when they don't run. So in 6, carton arrives at the entrance to the conveyor. Decision is to run the conveyor or wait for logical conditions. Well, it sounds like we're repeating, and we are, because the logical conditions can change between step 1 and step 6. Let's say the conveyor is only long enough to buffer 2 cartons, meaning to have 2 sitting on the conveyor and then consider the conveyor full. Now just in looking at the diagram, the illustration, you could probably squeeze another carton on there if you wanted to keep the cartons closer together. And what determines the singulation, the spacing, is where the photo eye is mounted, because remember the carton stops when the photo eye is clear. So the photo eye is very critical. It has to be in a position where a carton hitting the entrance of a dead conveyor blocks the photo eye, so you know there's one there, and far enough onto the next conveyor to leave you a little gap between the end of one carton and the beginning of the next. You want, some clear space between the cartons. So in step 7, carton arrives at the entrance to conveyor 2. In other words, we ran conveyor 1. So in the preceding step 6, if we went ahead and ran the conveyor, then the obvious conclusion is that those 3 cartons in step 6 are now going to hit the end, or I should say the entrance of conveyor 2. Carton arrives at the entrance to conveyor 2. Decision is to run the conveyors 1 and 2 or wait for logical conditions. Now, it's unlikely that you would run just conveyor 2 and not conveyor 1 to pull a carton onto conveyor 2, because there may be enough friction between the bottom of the carton and conveyor 1 that you can't extricate that first carton from conveyor 1 onto conveyor 2. Then in step 8, carton is at the entrance to conveyors 1 and 2. Decision is to run conveyors 1 and 2 or to wait for logical conditions. Obviously in step 8, you cannot run, well, you could run conveyor 1, but you know what's going to happen? If you're not running conveyor 2, then that carton in the lead will just push up against and maybe a little further up onto conveyor 2, and then it'll start slipping on conveyor 1, and then all the cartons behind it will catch up, and the 4th carton, the one that's coming on now, step 8, it won't clear the photo eye. It'll never clear the photo eye without running conveyor 2. So this is just a little primer to get you thinking in terms of cartons moving on conveyors. Assume that the photo eyes and the conveyor motors are non-reversing. That means that you don't have the benefit of a reversing starter equipment to reverse the direction of the motor. Assume that the photo eyes and the conveyor motors, non-reversing, are connected to the controller. After you have examined the above images, on the previous page and comments, answer these questions. What is the most that the controller's logic can see? The most that it can see is that whether there is or is not something in front of 1 PE and 2 PE. So if you close your eyes or imagine those 2 conveyors and something is blocking both photo eyes, it can't be the same carton, so it has to be 2 separate cartons, but that does not define or denote that there are any other cartons on those 2 conveyors but those 2, the 2 that are blocking those 2 photo eyes. Or if there's only 1 photo eye blocked, you could have a total of 6 cartons on those 2 conveyors. The controller doesn't know it. I mean, you can do things like you see right in front of you for counting up and counting down. What is the most that the controller can control? The most of the control is the on and off state of those motors, the motion of the conveyors. It can turn the conveyor on or off, so it has, really 4 things it can do. For nuances, 4 scenarios: conveyor 1 and 2 off, conveyor 1 on, conveyor 2 off, conveyor 1 off, conveyor 2 on, both conveyors on. There's 4 instances. Other than the obvious, conveyance from A to B, entrance conveyor 1 to exit conveyor 2, there are many different logical modes for controlling conveyors. We will examine just a few of many. The beauty of programmable controller is that you can write routines for many different modes and then logically select which mode best suits the upstream and downstream conditions. Here we have debounce timers of 1 second. Now we did 1 second. We dropped it from 2 just because I don't want to wait 2 seconds to see it time out. But you can actually have, we'll call it recipe management or process management where you move different values into those timer data types for those demounts timers based on what carton you're running or what product you're running. Okay, with one PE and one motor, each conveyor can pass through, which is pass the carton through to the next conveyor or station, or it can buffer. Stop the conveyor for each carton that has traveled onto the conveyor and wait for the next carton to arrive, as seen in step 2 on the previous page. Each conveyor can be programmed to do either as production calls for it. With 2 or more conveyors in series, they can transfer, run in a sequence to move a carton off of one and onto another. Just from the illustration, you can speculate whether or not conveyor 2 can pull a carton off of conveyor 1 without conveyor 1 running, pushing. I already covered that. And the question is, can you speculate? Well, yes, you can speculate. It probably won't. Conveyor 2 won't pull one off of conveyor 1 unless conveyor 1 is running and pushing it. With 2 more conveyors in series, those 2 conveyors can transfer. They can buffer. Conveyor 1 fills up first and then begins filling up conveyor 2 with each new arrival at the entrance of conveyor 1. Then there's weighted buffer, a modification of that. Conveyor 1 passes through to conveyor 2, which buffers cartons, or conveyor 1 can buffer and then pass through conveyor 2. So that gives you 3 options with those 2 conveyors. Both pass through, one buffer, well, actually 4. 2 conveyors pass through, 1 pass through, 2 buffer, 1 buffer, 2 pass through, or both of them buffer. Those are most of the limits to what you can do with sensors and non-reversing motors given in this application. Now, what are some of the things that you can do with the instruction set to go from instantaneous decisions, logic, to logic that includes time and space? With just a photo eye, can the controller know how many cartons are on each conveyor? No. How many cartons can a photo eye see? 1. If there are no photo eyes sensing cartons, does that indicate that there are no cartons on the conveyor? No. You could push a carton onto a conveyor and stop after a delay, using a timer instruction. Or, more deterministically, you could stop after the PE is clear of the carton. So you could use a timer to stop a carton before it clears and just use the photo eye to stop it when it clears, or you can use a timer to delay the conveyor motor stopping after the photo eye clears to lengthen the space between the cartons. How do you determine when the conveyor is full? Continue to transfer stop cartons until they reach the entrance PE at the next conveyor station. That's one way. The problem with that is if the length of your conveyors aren't well synchronized with the length of your cartons, you could end up with a situation with 3 cartons on a conveyor. A new one arrives at the entrance, the motor takes off, the leading carton breaks the photo eye of the next conveyor, but the 4th carton coming on to the entrance isn't clear of the photo eye. The conveyor stops and there the carton sits half on, half off. Or count each carton as it is transferred and then count them off when they transfer into the next station. You can even use math instructions to calculate when it is full based on conveyor runtime, speed, and time per event. What is the downside to each of these logical controls? When a conveyor arrives at the entrance PE of the next station, and this occurs while a carton at the entrance is not completely transferred onto the conveyor, what do you do logically? The singulation would have to be adjusted for each carton length to coordinate the available length of conveyor to the carton lengths. And I just explained that when we were talking about continue to transfer cartons until they reach the entrance PE at the next station. At that time, I discussed basically what they're giving you here for solutions. The singulation would have to be adjusted for each carton length to coordinate the available length of the conveyor to the carton lengths. In other words, you would have to increase or reduce the space between each carton. So there's no way you could have a carton partway on the next conveyor and have one partway on at the same time. In other words, on conveyor 1, you have one half on conveyor 1, and then at the other end of conveyor 1, you have it one half off and half on the next conveyor. You could adjust the singulation space to avoid that, which means you might have to really increase the space. In our images on the page before last, on those diagrams, you would have to increase it so you would never really have two at rest on the conveyor at a time. You'd have to space them out and say the conveyor is full when it's 2. The preset for the counter has to be set for the longest carton. And that's what basically the solution I just said. The preset for the counter would have to be adjusted for each type of carton to avoid losing valuable buffering space. With all this in mind, let's do something simple.